I'm doing a PhD in fluid mechanics. Mechanics is the study of how things move in time and space. For example, planets or particles. And fluid mechanics is obviously the mechanics of fluids, fluid particles. It's much more complicated than normal mechanics because there are so many different particles and so many unknown things. A good example of this is the eclipse back in '99. This was predicted to the minute by astronomers many centuries ago, but no one could tell you on the day whether or not the sky would be cloudy and you'd be able to see it. I'm looking at the flow of a fluid, let's say oil, between two spherical shells. So imagine you've got a big ball and you've got another ball inside, and the gap between the two is filled with an oil, say. Either of the balls can rotate in either direction they like, and the flow in the fluid is driven by these boundaries moving. And I have a partial differential equation that models the size of the instability in the flow, where the instability arises when the system is moving fast enough for there to be instability. At low speeds, you'll have a nice uniform, what we call laminar flow, and this breaks down to instability and in the end turbulence as you increase the speed. And instability of fluid is very important because sometimes it's wanted, sometimes it's not. If for example you're running a mixing system, say you're mixing aircraft fuel with air in an engine, you want as much turbulence as possible so you can mix the two fluids together. However, if you're looking at the flow of air over an aircraft wing, say, you want it to be nice and well behaved, and you don't want any turbulence because that can affect how the airplane flies.